Good evening and welcome to The Sleepy Scientist. If you're settling in for the night, this is your cue to slow your breathing, find a comfortable spot, and let your mind drift gently through the quiet corners of the universe. Tonight's story is about how everything around us, every galaxy, every snowflake, every heartbeat, emerged from chaos. This is the calm tale of how disorder became design, and how the universe learned to create patterns from noise. Before we begin, I'd love to know where in the world you're watching from tonight. It's always wonderful seeing this little community stretch across continents and time zones. If you enjoy these peaceful explorations of science, please do give the video a like and consider subscribing to the channel. And if you're already part of the Sleepy Scientist family, thank you so much for watching again. Please make sure to click the notification bell so you won't miss the next quiet journey through time, space, and science. I hope this video isn't so interesting that it keeps you awake, but if it does, at least you'll drift off a little wiser than before. So, how did the universe take the swirling chaos of its birth and turn it into stars, life, and thought itself? Let's begin the search for the moment when chaos became order. In the beginning, there was no pattern. No up or down, no matter or light. Just a restless sea of energy, expanding and cooling, full of potential, but utterly without form. And yet somehow out of that cosmic haze structure arose, atoms formed, galaxies spun, life bloomed. This is one of the most fascinating puzzles in all of science. Why the universe, despite its tendency toward disorder, seems so astonishingly good at creating order. Every atom in your body, every planet, every living thing, each is a small victory of organization over chaos. But the trick is that order doesn't defy chaos. It emerges from it, like music emerging from noise. When we speak of chaos, we often imagine confusion, randomness, and unpredictability. But in physics, chaos simply means sensitivity. Small changes that can lead to vast differences over time. And order isn't rigidity or control, it's coherence, the gentle rhythm that holds things together. The two are not opposites, they're partners in the great unfolding of reality. In the earliest moments of the universe, everything was uniform and symmetric. That symmetry didn't last long. As the cosmos cooled, it fractured. Tiny fluctuations grew, and out of those ripples came structure. From that first act of imbalance, everything we know began to form. It's as though the universe discovered that perfection was sterile and imperfection was creative. You can see that same pattern at every scale. Storms swirl from calm air, snowflakes crystallize from formless vapor, galaxies spin into existence from clouds of dust. Even your own thoughts are the result of chaotic electrical storms settling into ordered patterns of meaning. The story of order arising from chaos isn't just the universe's story, it's yours as well. Across the next chapters, we'll drift through that story step by step, tracing how laws of physics and chemistry, chance and feedback, gave rise to the beautiful complexity we see today. But for now, as you settle deeper into the quiet, keep this thought close. Maybe chaos was never the enemy of order. Maybe it was its teacher all along. Symmetry is one of those ideas that feels both mathematical and poetic. At its heart, symmetry means sameness. Something that looks unchanged even when you turn it, flip it, or move it around. A snowflake, for instance, mirrors itself along 6 delicate axes. The petals of a flower, the ripples in a pond, the spiral of a galaxy, all carry echoes of balance. Physicists love symmetry because it hints at simplicity. A symmetrical universe would be tidy, predictable, and elegant. But too much symmetry can be boring. Nothing happens, nothing differentiates one side from another. For anything interesting to exist, symmetry must be broken. Imagine the universe in its first moments after the Big Bang, a smooth uniform ocean of energy. There were no stars, no light or darkness, not even the familiar forces we know today. Everything was balanced so perfectly that there was, in a sense, nowhere to go. It was as if the cosmos were a coin balanced on its edge, motionless, waiting for a nudge, and then, imperceptibly, it tipped. As the young universe expanded and cooled, that perfect symmetry began to falter. Energy condensed into particles, and the laws of nature began to take shape. Forces that had once been unified, gravity, electromagnetism, and the nuclear forces, separated like colours splitting from white light. This process is known as symmetry breaking, and it is the reason the universe has variety. It is what gave the cosmos a direction to evolve in. You can think of it like this. When water cools and turns into ice, the molecules suddenly decide on a pattern. Before, they were free to move anywhere, shapeless and symmetrical. After freezing, they settle into a crystal lattice, breaking that freedom but gaining structure. The universe did something similar, except instead of ice crystals, it formed the scaffolding of reality. At each stage of cooling, a new kind of order emerged. When the universe was unimaginably hot, perhaps 1 trillion degrees, everything behaved the same. But as it cooled below certain thresholds, hidden differences appeared. One symmetry would break, revealing new particles or forces. Later, another would fracture. Each small imbalance created new possibilities, like a blank page gaining its first faint lines. It might sound strange to say that breaking symmetry created order, but that is precisely what happened. Perfect symmetry, though elegant, is sterile. It contains no information, no contrast. When symmetry breaks, the universe gains a sense of direction. Up versus down, matter versus antimatter, light versus dark. These distinctions are what allow structure to exist at all. Without that first imperfection, the universe would still be a featureless blur of energy. One simple image helps make sense of this. Picture a perfectly round hilltop. At the very peak sits a tiny ball. The hill is symmetrical. No direction is special, but the ball cannot stay balanced forever. The slightest disturbance, a quantum fluctuation, a breath of randomness, makes it roll one way. Once it starts, the symmetry is broken. The ball could have rolled anywhere, but it chose a path. The universe is that ball, and that small tilt is the origin of everything that followed. When physicists talk about the early universe choosing its layout, they do not mean it made a conscious decision. Rather, random fluctuations, tiny quantum jitters, pushed it into one of many equally possible configurations. Once that happened, the rest of cosmic history unfolded according to that choice. Every galaxy, every atom, every living thing traces its ancestry back to that first uneven moment. Symmetry breaking also explains why matter exists at all. In the earliest times, matter and antimatter were created in nearly equal amounts. When they met, they annihilated each other, leaving behind only light. Yet something curious occurred. For every billion pairs that destroyed each other, one extra particle of matter remained. That tiny imbalance, barely a whisper against the roar of creation, is the reason anything solid exists today. Every atom of your body is made from those leftovers of broken symmetry. The process continued as the universe aged. Within fractions of a second, fundamental particles appeared. Within minutes, they fused into the first atomic nuclei. Much later, those atoms gathered into stars and galaxies. But it all began with that first gentle distinction, that small deviation from perfection. In breaking its symmetry, the universe gained texture, depth, and meaning. The principle extends far beyond cosmology. Symmetry breaking shapes the behavior of magnets when they choose north and south. It governs how water forms ice, how liquids boil, and even how cells in your body decide where to grow. It is the quiet engine behind complexity, the reason patterns can appear in nature without anyone arranging them. In fact, you could say the universe is addicted to breaking symmetry. Each new layer of order it creates comes from letting go of a higher one. There's a kind of poetic irony in this. We tend to think of order as perfection, but the universe's idea of order is messier and far more interesting. Its balance disturbed just enough to allow creativity. Perfect stillness might look serene, but it cannot dance. It was only when the cosmic symmetry cracked that the first rhythm appeared, the rhythm that still hums through everything today. So, from that vast, silent equilibrium, a single tremor rippled outward, and from that tremor came structure, direction, and possibility. From perfect stillness, the first ripple of distinction. The story of the universe's first moments is one of astonishing quiet and equally astonishing chaos. Imagine the cosmos when it was smaller than an atom, filled not with matter, but with a restless sea of energy. Even at that scale, nothing was perfectly still. Quantum mechanics tells us that emptiness itself is never truly empty. It fizzes and trembles with tiny fluctuations, bursts of energy appearing and vanishing in unimaginably brief moments. These are called quantum fluctuations, and they are the background hum of existence. In that microscopic beginning, these fluctuations were insignificant, mere whispers in the void. But they were also inevitable. The uncertainty that rules the quantum world means energy cannot remain perfectly uniform. A momentary increase here, a tiny dip there. This randomness is woven into the fabric of reality, and yet those faint irregularities would one day become the reason galaxies exist. Shortly after the universe's birth, something extraordinary happened. Space itself began to expand at a staggering rate in an event known as cosmic inflation. In a fraction of a second, the universe grew exponentially, stretching from subatomic size to something vast enough to contain everything we now see. During this incredible expansion, those microscopic quantum fluctuations were stretched along with space, magnified billions upon billions of times. What were once infinitesimal ripples became the first seeds of structure. You could think of inflation as the universe taking a deep breath. In that breath, it smoothed itself out, ironing away much of its early chaos, but not completely. Those quantum ripples remained, frozen into place as slight variations in density, tiny pockets where energy was a little higher or lower than average. Over time, gravity began to notice those small differences. Denser regions pulled in more matter, growing heavier, while lighter areas became the great voids between galaxies. In that sense, every star, every planet, and every living thing owes its existence to the randomness of quantum fluctuations, stretched across space by inflation. The universe, it seems, did not begin with a plan. It began with noise, and from that noise patterns emerged. It is difficult to imagine the scale of this process. The fluctuations themselves were smaller than atoms, yet the inflationary expansion made them cosmic in size. When astronomers look at the faint afterglow of the Big Bang, the cosmic microwave background, they can still see the imprint of those ripples. Subtle variations in temperature, no more than a few parts in 100,000, are the fingerprints of quantum murmurs amplified to astronomical proportions. That map of ancient light is like a baby picture of the universe, showing where matter would one day gather to form galaxies. It's a beautiful thought that the Milky Way, the galaxy that cradles our sun, began as a slightly denser region in an almost perfectly uniform sea of energy. Without those tiny imperfections, gravity would have had nothing to work with. no starting point from which to weave the grand structures of the cosmos. In a perfectly smooth universe, there would be no stars, no planets, and no life to wonder about any of it. Order needs just a hint of chaos to begin. The mechanism of inflation itself is still one of physics' great mysteries. What drove it? Some theories suggest that a special field called the inflaton filled the early universe and suddenly released its energy, propelling space outward faster than the speed of light, not moving through space, but expanding space itself. Others propose variations on that theme, but all agree that inflation explains the remarkable uniformity we see across the cosmos and the small imperfections that led to everything. The idea that quantum randomness could sculpt the structure of the universe may sound almost absurd. How could something so vast arise from something so uncertain? But that is one of the quiet wonders of physics. Scale changes everything. What begins as a flicker at the quantum level can become an entire galaxy when the stage is large enough. Randomness, when given time and space, finds a way to create form. Those first ripples in density were unimaginably subtle, but over billions of years gravity turned them into the grand architecture of the cosmos. Regions with slightly higher density pulled in more gas, forming the first stars. Stars gathered into galaxies, galaxies into clusters, and clusters into the cosmic web that stretches across the universe today. All of it, the Milky Way, the Andromeda Galaxy, the distant quasars shining billions of light years away, began as faint patterns of unevenness in an ocean of quantum energy. If you could somehow replay the universe from the beginning, letting inflation unfold again with a slightly different pattern of quantum noise, the galaxies would form in new arrangements, stars would shine in different places, and perhaps even entirely different histories of life would play out. The cosmic tapestry we see today is only one version of countless possible designs that could have emerged from those early murmurs. When you look up at the night sky, every glittering point of light represents a triumph of randomness, the physical echo of quantum uncertainty scaled up to cosmic proportions. The order of the heavens is built on the most delicate foundation imaginable, the vibrations of nothingness. In a poetic way, it's comforting to know that even the universe's grandest designs began as a collection of tiny, uncertain moments. For billions of years, gravity has been amplifying those faint imbalances, turning the once featureless universe into a masterpiece of complexity. Yet beneath it all lies the same gentle hum of uncertainty that started it. Every atom still vibrates with that quantum restlessness. The patterns we see are just frozen echoes of it, shaped into stars and planets and people. The universe began as static, then trembled into design. Out of the smallest possible fluctuations it found its rhythm, and in that rhythm it built everything that is. What began as whispers in the quantum dark became the luminous pattern of the cosmos, a quiet reminder that even the grandest structures are born from uncertainty, and that order itself is just chaos, patiently refined. Gravity is the quiet artist of the cosmos. It does not blaze or roar, it does not rush or shout, it simply waits, pulling gently, endlessly patient, shaping everything that exists through persistence alone. Where other forces act in flashes, sudden, powerful, and fleeting, gravity works like a slow tide, subtle but unstoppable. After the early universe had stretched and cooled, it was still mostly uniform. Vast clouds of hydrogen and helium gas spread almost evenly across expanding space. The differences between one region and another were unimaginably small, 1 part in 100,000. But gravity is sensitive to difference. Even a tiny excess of matter in one spot creates a slightly stronger gravitational pull. That spot draws in more material, making it even denser, which strengthens its gravity further. Slowly that region grows heavier while its surroundings thin out. The rich get richer, cosmically speaking. This quiet feedback loop, small differences growing over time, is the reason the universe developed structure at all. Without gravity's steady hand, everything would have remained a smooth glowing mist. Instead it began to clump, forming knots and filaments, the first outlines of what would become galaxies. Gravity, in its calm, deliberate way, transformed chaos into architecture. It is difficult to imagine the patience involved. From the perspective of a human lifetime, gravity's pace is glacial. It took hundreds of millions of years for the first clouds of gas to collapse enough to ignite stars. Yet across cosmic time, its persistence is breathtaking. Gravity never hurries, yet it shapes everything. As the first dense regions grew, their pull gathered vast amounts of gas. Under the weight of that attraction, the gas heated up, compressing until its atoms fused. The first stars were born in these glowing pockets of order. Each star in turn became a miniature engine of change, fusing hydrogen into heavier elements, shining light across the darkness, and seeding the next generation of structure. Gravity's influence spread outward, turning simple clouds into organized systems. But gravity doesn't just pull things together, it also sets them in motion. When matter falls inward, it rarely does so in perfect alignment. Slight twists or differences in momentum cause the collapsing gas to spin. This rotation prevents everything from crashing into a single point. Instead, material flattens into rotating disks, cosmic whirlpools that form the graceful spiral arms of galaxies. Gravity, acting together with motion, finds balance. The inward pull of attraction is matched by the outward tendency of motion, creating stable, enduring structures. Our own Milky Way is a masterpiece of this balance. Billions of stars orbit its center, each held in place by gravity but kept from falling inward by their motion through space. The result is a grand spiral, turning slowly over hundreds of millions of years, every glowing star in its arms, every drifting cloud of gas, every planet circling its sun, each is part of a gravitational dance so vast and slow that we can only glimpse its beauty in snapshots of stillness. On smaller scales, the same pattern repeats. Within galaxies, gravity pulls gas together into dense regions where new stars are born. Around those stars, leftover material forms disks that eventually give rise to planets, moons, and asteroids. The same principle that built galaxies also sculpted our solar system. It is as if the universe keeps reusing its favourite rule: pull gently, allow motion, and let time do the rest. There is a delicate harmony in how gravity and motion interact. If a planet moves too slowly, it spirals inward and is consumed. If it moves too quickly, it escapes altogether. But when those forces balance perfectly, the result is an orbit, a serene loop that can last for billions of years. It's a cosmic form of cooperation. Gravity provides the structure, motion provides the freedom. Together, they maintain order without ever needing perfection. The shapes gravity creates are often surprising. Galaxies, for instance, are not static clusters but dynamic ecosystems. Stars orbit in vast patterns, clusters merge and collide. Dark matter forms halos that extend far beyond visible light. Even the gaps and voids between galaxies are part of the design. Gravity sculpts not just the things we see, but the spaces in between, giving the universe its grand web-like structure, a network stretching for billions of light years, linking clusters with filaments like a cosmic lacework. And yet, for all its reach, gravity is the weakest of the known forces. A small magnet can lift a paperclip against the entire pull of the Earth. But what gravity lacks in strength, it makes up for in endurance. It never turns off, never screens itself out, and its influence extends infinitely. Over time, that weakness becomes a virtue. Where other forces cancel or fade, gravity accumulates. It binds stars into galaxies, galaxies into clusters, and clusters into the vast cosmic web. If you zoom out far enough, you can almost see its handiwork as texture. Threads of galaxies weaving through enormous voids. The pattern resembles something living, veins, rivers, or neural pathways stretching through the night. All of it formed through countless years of patient attraction, the universe slowly knitting itself together from the inside out. There is also a quiet poetry in how gravity governs endings as well as beginnings. The same force that builds stars also guides their deaths. When a massive star burns through its fuel, gravity takes over again, pulling it inward. Sometimes this collapse creates a neutron star, a city-sized core of unimaginable density. Sometimes it forms a black hole, a place where gravity curves space so steeply that even light cannot escape. These remnants, in turn, shape their surroundings, pulling nearby matter into spiraling disks and launching jets that light up the cosmos. Even in destruction, gravity creates beauty. In a sense, gravity is less a force and more a conversation. It responds to mass and energy, curving the fabric of space-time around them, and in doing so tells everything how to move. Matter follows that curvature, and its movement reshapes the curvature in return. This feedback loop, the constant dialogue between matter and the geometry of space, is what keeps the universe coherent. It is not a rigid hierarchy, but an ongoing relationship between form and motion, from galaxies to planets, from tides to the fall of an apple. Gravity weaves the same story in countless variations. It's the slow melody underlying every movement in the universe, a rhythm so steady that it feels like silence until you listen closely. And when you do, you realize that everything, every orbit, every sunrise, every drifting cloud, is part of the same cosmic choreography. If you could speed up time, compressing billions of years into a single moment, the universe would seem to flow like liquid silk. Galaxies would twist and merge, stars would burst into light, and clusters would drift and reshape. You would see gravity's hand at work, endlessly weaving the threads of creation. Gravity never hurries, yet it shapes everything. It is the most patient sculptor imaginable, building, balancing, and refining across eternity. It takes the smallest differences and turns them into worlds, takes chaos and turns it into order. In the quiet persistence of its pull, the universe finds its form. Most of the universe is invisible, not hidden behind dust or distance, but truly unseen, made of something that does not glow, absorb or reflect light. This mysterious substance is called dark matter, and although it cannot be observed directly, its presence is unmistakable. It reveals itself through gravity, tugging on stars and galaxies, shaping the very fabric of the cosmos. You might say it is the universe's ghostly architect, building the stage upon which everything luminous performs. When astronomers first mapped how galaxies rotate, they noticed something strange. The stars at the edges moved far too quickly to be held together by the gravity of visible matter alone. If galaxies were made only of the stuff we can see, stars, gas and dust, they should have torn themselves apart long ago. Something unseen was providing extra gravitational glue, keeping everything bound. That hidden mass became known as dark matter. It turns out that this invisible material makes up the vast majority of the universe's matter. For every bit of ordinary atoms, everything that forms stars, planets and people, there are about 5 times more of this unseen kind. It neither emits light, nor interacts much with it, which makes it extraordinarily difficult to detect. Yet its gravitational influence sculpts the cosmos on every scale. In the early universe, when matter was still spread thinly across expanding space, dark matter began to gather first. Unlike ordinary particles, which were slowed and scattered by radiation, dark matter was largely unaffected. It clumped together quietly, forming enormous halos of invisible mass, cosmic wells of gravity that would later attract ordinary gas. These halos became the skeleton of the universe, the dark scaffolding upon which galaxies would grow. As billions of years passed, gravity pulled streams of dark matter into an intricate network. Computer simulations show this structure as a vast cosmic web, long filaments linking dense nodes with enormous voids in between. Where filaments intersect, galaxies form, drawn to the gravitational hubs created by dark matter. It is as if an invisible hand traced the outlines of creation, sketching a framework before the stars ever began to shine. The beauty of this idea lies in its subtlety. We cannot see dark matter, but we can watch how it bends light from distant galaxies, distorting their shapes through a phenomenon called gravitational lensing. By studying these distortions, astronomers can map the distribution of dark matter as though painting a portrait of something transparent. These maps reveal that every luminous structure, every cluster, every spiral galaxy is wrapped in a vast halo of unseen mass, extending far beyond the reach of its stars. Without this hidden scaffolding, the universe would look very different. Ordinary matter, influenced by radiation pressure in the early cosmos, would have struggled to clump together on its own. The presence of dark matter provided the deep gravitational wells needed for gas to collect and cool. It was within these invisible frameworks that the first galaxies formed, where the first stars lit up and began forging the elements of life. In that sense, dark matter is the quiet enabler of everything visible. It made the stage before the lights turned on. And yet, for all its importance, we still don't know what dark matter actually is. It is not made of protons, neutrons, or electrons. It does not fit into the familiar pattern of the periodic table. Scientists have proposed many candidates: weakly interacting massive particles, axions, sterile neutrinos, even primordial black holes left over from the universe's earliest moments. Each idea comes with elegant mathematics and elaborate experiments designed to test it. So far, nature has remained silent. The search continues deep underground and high above the Earth. In underground laboratories shielded from cosmic rays, detectors wait patiently for a single dark matter particle to collide with an atomic nucleus. In orbit, telescopes scan the sky for faint signs of dark matter's decay or annihilation. And in vast computer models, scientists recreate universes from scratch, adjusting parameters to see which combinations produce galaxies like our own. Slowly the picture sharpens, even if the actor remains unseen. Dark matter's influence extends even into the behavior of galaxy clusters. When two clusters collide, the hot gas, made of ordinary atoms, slows down and lags behind. But the gravitational field traced by dark matter moves ahead. Astronomers can see this separation by studying how the cluster bends light, confirming that most of the mass lies not in visible gas, but in something invisible and faster moving. It is as though the universe is showing us the shadow of an object we cannot touch, giving hints about its form through its footprints. There's something almost philosophical about the whole affair. We often think of what is visible as what is real, and what is invisible as imagination. Yet the cosmos reminds us that the opposite can be true. What we cannot see may be the very thing that holds everything else together. Every glittering star, every glowing nebula, every swirling galaxy owes its stability to this unseen foundation. The universe, for all its brilliance, rests upon darkness. Dark matter also reveals a kind of cosmic humility. The stuff we're made of, atoms, molecules, and light, is a minority ingredient, a decorative layer on top of something deeper and quieter. It humbles our sense of scale. We are creatures built from the rarer fraction of the universe, peering out into a world whose true substance remains unknown. Yet that mystery doesn't diminish the beauty of the night sky. It enriches it. The next time you look at the Milky Way, remember that for every star you see, there are countless invisible particles shaping its path. In recent years, new ideas have emerged that may challenge even our current understanding. Some physicists wonder if dark matter might not be a new kind of particle at all, but instead a sign that our theory of gravity needs refining. Maybe space-time itself behaves differently on cosmic scales. Others propose that dark matter interacts with itself through forces we have yet to detect, forming its own shadowy versions of galaxies and clusters, parallel to our own but hidden forever from light. Whatever the answer turns out to be, one thing is certain. Without dark matter, there would be no galaxies, no stars, and no us. It is the universe's scaffolding, invisible but essential, the quiet structure upon which everything visible depends. It neither shines nor shouts for attention, yet it is everywhere, holding the cosmos together in its gentle grip. An invisible hand tracing the outlines of creation. That is dark matter's legacy. A silent partner in every act of cosmic design, unseen yet undeniable. It reminds us that sometimes the most profound truths are the ones that hide behind the light. Entropy is one of those words that seems to cause instant confusion. It's often described as disorder, which makes it sound like the universe is slowly turning into a messy teenager's bedroom. In truth, entropy isn't about clutter at all. It's about possibility, the number of ways a system can arrange itself. A state of high entropy simply means there are more possible configurations, while low entropy means fewer. The universe tends to move from the improbable to the probable, from the neatly arranged to the freely wandering. But that doesn't mean order can't appear. It just means that order must pay its dues. When the universe began, it was in a state of astonishing simplicity. Everything was hot, dense, and uniform. But as it expanded and cooled, complexity began to rise. Stars formed, galaxies spun, planets coalesced. How could all this structure exist in a universe supposedly ruled by a law that favours disorder? The answer lies in a subtle truth. While total entropy always increases, small pockets of order can emerge as long as the overall balance tilts toward greater chaos. The universe, in other words, can afford a few organised corners as long as it compensates elsewhere. Think of entropy as a kind of cosmic accountant. You can build order, but you have to pay for it, and the fee is always paid in heat. Whenever something becomes more structured, a snowflake forming from vapour, a cell assembling proteins, or a planet cooling and solidifying, energy is released into the surroundings, increasing entropy overall. The second law of thermodynamics doesn't forbid order, it simply keeps the books balanced. Entropy allows order. It just charges a small fee in heat. Earth is a perfect example of this principle in action. From space, our planet is a glowing blue oasis of order in a vast dark expanse. It hosts forests, oceans, weather systems, and an endless variety of living things. Yet all of this structure exists because Earth is not a closed system. It constantly receives energy from the sun, a steady flow of low entropy radiation in the form of sunlight. That energy drives the winds, the tides, and the endless cycles of chemistry that sustain life. The Earth then radiates this energy back into space as heat, which carries much higher entropy. The difference between the ordered energy arriving from the sun and the disordered energy leaving the Earth is what keeps everything running. In a sense, life is what happens while entropy tries to get its work done. The sun's rays come in neat, concentrated lines, and we scatter them into random warmth. The price of every growing plant, every thought, every heartbeat, is a tiny rise in cosmic disorder. Life, far from defying entropy, depends on it. Living systems are masters at creating local order, cells, organs, organisms, but they can only do it by exporting entropy to their surroundings. A growing seedling, for example, transforms simple molecules into complex tissues, but it releases heat and waste in the process. The total disorder of the system plus its environment still increases. Life doesn't cheat the universe's rules, it simply negotiates clever deals within them. The same principle explains everything from hurricanes to humans. A storm, for instance, forms because warm air and cold air meet, setting up a flow of energy that creates temporary order. The swirling eye of a hurricane is a local drop in entropy, a beautifully organized vortex, but once the energy difference that drives it is spent, the system dissolves back into calm air. Order appears and fades, a transient pattern in a larger sea of randomness. You can even see entropy at work in your morning coffee. When you pour cold milk into hot coffee, the swirls that appear are mesmerizing, beautiful structures of contrasting temperature and color. But those swirls don't last. The milk and coffee mix until everything becomes uniformly warm and brown. What's happening is entropy increasing. Energy is spreading out, temperature differences are evening, and the system is moving toward equilibrium. The swirling order exists only because of the imbalance between hot and cold. Once that imbalance is gone, so is the pattern. The same story plays out across the universe. Stars form when gravity compresses clouds of gas, releasing energy as heat and radiation. Galaxies organize themselves through gravitational attraction, while their internal chaos, collision, supernovae and stellar winds, spreads energy outward. Everywhere you look, order emerges as a byproduct of energy flow. The universe creates complexity not in spite of entropy, but because of it. Entropy can even be seen as the engine of creativity. Without the constant tendency toward equilibrium, there would be no gradients to drive motion, no differences in temperature or pressure to power change. Everything would be static and lifeless. It is precisely because things move toward disorder that processes like weather, chemistry, and life exist at all. Order, in this view, is entropy's way of burning off imbalance efficiently. There's also something comforting in knowing that the universe allows moments of order in its relentless drift toward chaos. The fact that we can sit here, thinking about entropy, means that somewhere along the way, energy was borrowed from a larger flow to create brains capable of reflection. We too are temporary structures, brief arrangements of atoms that will one day scatter back into simpler forms. But while we exist, we participate in the universe's grand balancing act, transforming concentrated sunlight into thought and warmth. On a cosmic scale, the universe's overall entropy is increasing as stars burn their fuel and radiate energy into the cold depths of space. One day, in the far distant future, those energy gradients will be exhausted. The stars will fade, galaxies will grow dark, and the cosmos will settle into a quiet equilibrium, a state often called the heat death. It sounds grim, but even that final stillness is a form of completeness. Entropy will have done its work. In the meantime, we live in the universe's dynamic Middle Age, where gradients still exist and order still blooms. Planets orbit, storms swirl, and life flourishes because the cosmos hasn't yet settled into calm. We are lucky enough to exist in a time when entropy's paradox is most vivid, a universe expanding, cooling, and yet constantly creating intricate patterns within its flow. The next time you see sunlight filtering through leaves, or watch a candle flame dance, remember that both are moments of borrowed order, paid for by the gentle spread of energy elsewhere. Entropy doesn't destroy beauty, it makes it possible. Without the constant dispersal of energy, nothing would change, and change is what gives life meaning. Entropy may be the universe's rule of disorder, but it also writes the poetry of transformation. It allows stars to shine, rivers to flow, and minds to dream, all while keeping its quiet account of energy paid and spent. In the grand story of existence, order is not a violation of entropy. It's the most elegant expression of it. Everywhere in nature there are moments when things suddenly change their minds. Water, so fluid and free, stiffens into solid ice. Metal loses its magnetism in a flash of heat. Air currents that once flowed smoothly erupt into turbulence. These are phase transitions, nature's pivot points, where the familiar laws of one world give way to the rules of another. They remind us that order doesn't always appear gradually. Sometimes it emerges in a single elegant step, as if the universe takes a deep breath and rearranges itself. A phase transition occurs whenever a system shifts from one state of organization to another. The simplest example is water freezing. As the temperature drops, molecules that were once tumbling chaotically begin to line up, forming the ordered lattice of ice. The transformation happens at a very specific point, 0 degrees Celsius at normal pressure, and it's sharp. Just a moment before, the liquid still flows freely. A moment later, it has become rigid crystal. The ingredients are the same, but their relationships have changed. The rules that govern their behavior have been rewritten. You can think of it as nature's version of a plot twist. For a long time, everything seems stable, predictable, and then, suddenly, there's a turning point. That turning point is what physicists call a critical point, the boundary between two forms of order. What makes it fascinating is that right at this edge, the system becomes exquisitely sensitive. Tiny fluctuations that would normally be ignored start to matter. Small causes produce large effects. It's as if the universe leans in close, holding its breath. One of the most beautiful things about phase transitions is their universality. The same mathematics that describes water turning to ice also applies to magnetism, to superconductivity, to the way crowds behave, or even to how traffic jams form. At a certain threshold, systems stop behaving as isolated particles and begin to act collectively, as if guided by a single invisible mind. Below a certain temperature, the magnetic moments in a piece of iron, which were once pointing in random directions, suddenly align. Above that temperature, they drift apart again. The transition between the two is smooth but profound, a moment when individual parts surrender their independence to become something larger. It's a little humbling to realize that such dramatic change can come from such simple ingredients. No new particles appear, no external command is given, and yet the system transforms. The same atoms, obeying the same physical laws, find new ways to cooperate. It's as though order has been hiding inside the chaos all along, waiting for the right conditions to step into the light. At the heart of every phase transition lies a balance between energy and entropy. When the temperature is high, motion dominates. Molecules bounce and spin too wildly to settle into any pattern. As things cool, movement slows, and the attractive forces between particles begin to matter. They start to prefer certain arrangements, trading some freedom for stability. Eventually, that preference wins, and the system crosses the threshold into a new state. Order emerges not through force, but through compromise, a gentle negotiation between energy and stillness. If you zoom in near the critical point of a phase transition, you see something remarkable: fluctuations on every scale. In a magnet approaching its critical temperature, small clusters of aligned atoms appear and disappear constantly. Some are tiny, others are large, but there's no single characteristic size. This scale-free behavior is one reason physicists find critical points so enchanting. They sit halfway between randomness and structure, where everything seems to echo everything else. Patterns repeat themselves in miniature, like fractals written in motion. These fluctuations are not confined to physics. The same self-similar behavior can be found in economics, ecosystems, and even human creativity. When systems approach a critical point, when they're about to change, they often display bursts of activity at every scale. It's the telltale sign of a system poised between the old and the new. Chaos and order mingle there, neither fully in charge. It's the universe in the act of deciding. There's also a certain grace in how reversible these transformations can be. Warm ice and it melts back into water, cool water and it freezes again. Yet each crossing of that threshold carries drama. The molecules rearrange themselves as though remembering a dance learned long ago. It's easy to overlook the artistry in something so common, but the symmetry of a snowflake or the shimmer of frost is a visible trace of that molecular choreography. Other transitions are more mysterious. When certain materials are cooled close to absolute zero, their electrical resistance vanishes completely. They become superconductors, carrying current without loss. No single atom causes this. Instead, electrons pair up in a delicate quantum waltz, moving as one coherent whole. This is another kind of order born at the brink, a new state of matter where individuality gives way to unity. The same principle shows up in magnetic transitions. When a piece of iron cools below its Curie temperature, its atomic magnets align, and the material suddenly becomes magnetic. That instant of alignment creates an emergent property, a collective strength that didn't exist in any single atom. Warm it up again, and that unity dissolves back into randomness. The edge between these two states is razor thin, yet worlds apart in behavior. It's tempting to see these transformations as metaphors for change in life itself. Often stability lasts for a long time. Then, suddenly, conditions shift and something new emerges. Growth, learning, and even social change have their own critical points, moments when small actions can ripple through a system and cause large transformations. In nature, as in life, order often hides on the edge of transformation. One of the most captivating things about studying phase transitions is how they reveal unity across the universe. The same elegant equations describe boiling water, magnetizing iron, and the birth of galaxies. In each case, the transition is marked by collective behavior, individual components acting together without a leader, finding new patterns spontaneously. It is as if the cosmos enjoys recycling its rules, playing variations on a single theme of transformation. At a deep level, these transitions hint at how the universe builds complexity. Every time matter reorganizes, new kinds of order become possible. The freezing of water allows solid landscapes to form. The alignment of magnetic fields helps guide cosmic rays and shape star formation. Even the transitions inside atomic nuclei and stars determine the elements that fill the periodic table. Phase transitions are the punctuation marks in the story of creation. The moments when the universe pauses, shifts tone, and continues on a new path. And yet, despite the complexity they produce, their underlying simplicity is remarkable. The same atoms, governed by the same forces, can be a gas, a liquid, or a solid, depending only on temperature and pressure. It's a quiet reminder that change doesn't require new ingredients, just new relationships. Next time you watch frost forming on a window, or steam curling from a cup of tea, remember that you are witnessing one of nature's quiet revolutions. Beneath the gentle shimmer of ice or the graceful twist of vapor lies an ancient rhythm of transformation, a dance between chaos and order, energy and calm. Order often hides on the edge of transformation, waiting for just the right moment to appear. In those fleeting transitions, the universe shows its hand, reminding us that every boundary between solid and liquid, between one idea and the next, is not an end but a doorway. In the quiet world of chemistry, order can appear out of nowhere. Imagine a dish filled with colourless chemicals that suddenly begins to ripple with shifting blues and purples, forming rings, spirals, or spots that move and change over time. No hand guides them, no pattern is drawn. The chemicals themselves decide how to arrange. This is the strange beauty of reaction diffusion systems, patterns that paint themselves. At first glance, it seems impossible that something so structured could come from such simplicity. After all, chemistry is supposed to be about molecules bumping into each other at random, reacting wherever they meet. Yet under the right conditions, randomness gives way to rhythm. Certain combinations of reactions and diffusion, the way chemicals spread through space, can produce stable, repeating designs. It's as if the molecules start whispering to one another, agreeing where to gather and where to retreat, composing patterns that persist long after the initial reaction begins. This idea might sound poetic, but it is grounded in hard mathematics, thanks to a man better known for something entirely different. Alan Turing, the mathematician famous for helping to crack the Enigma code during World War II, spent his later years pondering a biological puzzle. How does a simple embryo made of identical cells develop complex structures like stripes, spots, or spirals? What invisible hand tells certain cells to become skin, others to become hair, and still others to form pigment? Turing proposed that the answer lay not in some pre-existing blueprint, but in the chemistry of life itself. He imagined two substances, an activator and an inhibitor, reacting and diffusing through a field of cells. The activator would encourage its own production, as well as that of the inhibitor, while the inhibitor would diffuse more quickly, suppressing the activator in nearby regions. The push and pull between these two forces, Turing reasoned, could create stable, repeating patterns all on their own. The math was elegant. It showed that under the right conditions, random fluctuations could grow into distinct shapes, a leopard's spots, a zebra's stripes, or the spiral of a seashell. The secret lay in timing. If diffusion and reaction rates balanced just so, order would emerge spontaneously from the noise. It was a revolutionary idea that complexity could arise without instruction, without genes predetermining every detail. Life, Turing suggested, could design itself. For years, Turing's insight was overlooked. His equations seemed abstract, and in the 1950s no one had the tools to test them, but decades later experiments began to prove him right. Chemists discovered mixtures of reacting chemicals that produced Turing-like patterns in real time. The Blusov-Jabotinsky reaction, for instance, can create pulsing waves of colour that spiral and oscillate like a living heartbeat. Even in lifeless beakers, Turing's mathematics came alive. The visual results are mesmerising. In one region, small dots emerge and fade, while in another, stripes ripple outward like the rings on water. Sometimes the patterns move and change as though the chemicals are breathing. It's a kind of chemical choreography, each molecule responding only to local rules, yet together forming a global design. This is order as nature's slow exhale, a patient release of structure from the lungs of chaos. These patterns are not limited to the laboratory. In the natural world they appear everywhere once you know where to look. The stripes on angelfish, the spots on leopards, the spirals on tropical shells, all follow the same underlying logic. Pigment cells in developing embryos interact like Turing's activator and inhibitor chemicals. Where the activator dominates, pigment forms. Where the inhibitor spreads faster, the colour is suppressed. The result is an intricate map drawn not by an artist's hand but by diffusion and timing. Even the branching veins of leaves and the ridges on sand dunes echo these dynamics. When competing processes, growth and diffusion, accumulation and dispersal, reach balance, the universe begins to decorate itself. It doesn't need intention, it just needs contrast. Wherever two tendencies meet, one that builds, one that spreads, pattern follows. What makes this phenomenon so fascinating is its mix of inevitability and unpredictability. The overall form, the stripes, the spots, the spirals, feels familiar and orderly, yet the exact placement of each feature is unique. No two tigers have identical stripes, and no two seashells spiral in precisely the same way. The rules are universal, but their outcomes are endlessly varied. Nature repeats its grammar, but never its sentences. You could say that reaction-diffusion patterns represent the middle ground between chaos and control. If reactions were too fast, the system would explode into uniform chaos. If diffusion were too strong, everything would blend into boring uniformity. But somewhere between these extremes lies a delicate equilibrium, where new forms continually arise and sustain themselves. That middle ground is where nature seems to do its best thinking. The implications of Turing's discovery reach far beyond biology. Scientists now use reaction-diffusion models to understand coral growth, mineral crystallization, chemical waves in the brain, and even traffic flow and social dynamics. The same mathematics that explains a jellyfish's rings can describe how urban patterns form, how diseases spread, or how sand ripples across a desert floor. Turing had uncovered a universal principle of self-organization, one that bridges chemistry, physics, and life itself. It's humbling to realize that the same laws guiding a patch of reacting chemicals also shaped the natural world that inspired cave paintings, art, and architecture. The stripes of a zebra are not so different in spirit from the tiles of a cathedral or the ripples in windblown sand. Each is a conversation between forces, a dialogue between motion and stillness, growth and decay, chaos and symmetry. If you zoom in closely enough, the story grows even more elegant. Each molecule, moving on its own, knows nothing of the larger pattern. It follows only simple rules of reaction and diffusion, yet together they generate complexity that seems purposeful, almost intelligent. This is emergence in its purest form, order not imposed from above, but arising naturally from below. It's a reminder that the universe doesn't need blueprints to build beauty, it just needs balance. There's something calming about this idea. The same mathematics that explains the colour of a fish or the whirl of a snail shell also underlies the clouds in the sky and the chemical processes in your body. Patterns arise because the universe can't resist them. Given energy, time, and the right conditions, chaos becomes creative. So the next time you notice the dappled pattern of sunlight through leaves, or the way frost spreads across a window, think of Turing's insight, the delicate interplay between reaction and diffusion. Those patterns, like so many in nature, are nature's way of exhaling, releasing tension in graceful geometry. Order as nature's slow exhale. That's what these systems reveal, the quiet, inevitable beauty that emerges when opposites meet halfway, when the universe, for a brief and balanced moment, learns how to paint. Chaos is one of those words that seems to promise complete disorder. We imagine storms, tangled wires, or messy rooms, things that resist control or prediction. But in the language of science, chaos doesn't mean pure randomness. It means something far more intriguing. Systems that are fully determined by physical laws, yet behave in ways that appear unpredictable. Beneath the apparent disorder, there is structure. Beneath the noise, there is a pattern. The roots of chaos theory go back to a simple question. Why is weather so hard to predict? In the early 1960s, meteorologist Edward Lorenz was running computer simulations of atmospheric convection. how air rises and falls as it warms and cools. One day, he decided to restart a simulation halfway through by typing in the numbers from a printed page instead of the computer's internal memory. The results diverged dramatically. What should have been nearly identical weather patterns quickly became completely different. Lorenz realized that tiny differences in initial conditions, so small they might be rounded off, could lead to huge differences in outcome. This became known as sensitive dependence on initial conditions, or more poetically, the butterfly effect. The idea that a butterfly flapping its wings in one place could influence a hurricane on the other side of the world. It doesn't mean that butterflies control the weather, of course, but it does illustrate how complex systems can amplify small causes into vast consequences. Chaotic systems like this are deterministic. They follow precise laws of physics. If we knew every detail with infinite accuracy, we could, in principle, predict their behavior perfectly. But in practice, we never can. The tiniest rounding error or overlooked detail grows exponentially with time until prediction becomes impossible. What makes chaos fascinating is that this unpredictability doesn't come from randomness. It comes from too much sensitivity. Lorenz's equations describing air circulation produced patterns that, when plotted in 3 dimensions, formed a shape of haunting beauty, a swirling double spiral resembling butterfly wings. The system's behavior never repeated, yet it also never strayed outside this shape. No matter how wildly the simulated weather shifted, its path always curved back toward the same intricate form. This was the first strange attractor, a concept that lies at the heart of chaos theory. An attractor in physics is a set of conditions that a system tends to settle into over time. For example, a swinging pendulum eventually comes to rest at its lowest point. That's a simple attractor. But in chaotic systems, the attractor isn't a single point or a simple loop. It's a complex folded structure, infinitely detailed, never repeating, yet confined. Like the Lorenz attractor, it traces out a pattern in space that seems to breathe and flutter endlessly. Chaos doesn't wander aimlessly. It dances within invisible boundaries. You can find examples of this everywhere. The weather itself is one vast chaotic system, governed by equations far too sensitive to solve in full detail. The flow of water, the flicker of flames, the beating of your heart, all display chaotic rhythms that appear irregular but are bound by hidden rules. Even the motion of a simple pendulum, if you link 2 arms together into a double pendulum, becomes chaotic. Its movement seems erratic, yet if you plot its path through time, you'll find it looping through a shape of surprising regularity, a strange attractor of its own. What makes strange attractors so mesmerizing is their fractal nature. Zoom in, and you see smaller copies of the whole pattern repeating endlessly, each scale revealing finer structure. This self-similarity means that chaos, rather than being the absence of order, is a deeper kind of order, one that thrives in complexity. It's like discovering that noise has a melody after all, but one that takes infinite patience to hear. There's also a philosophical beauty to chaos. It shows that determinism doesn't guarantee predictability. The universe can obey strict laws and still be full of surprises. The clockwork precision once imagined by early scientists gives way to a softer vision, one where order and uncertainty coexist, intertwined. In chaotic systems, even though we cannot forecast specific outcomes, we can still understand the shape of their possibilities. That shape, the strange attractor, is like a fingerprint left by nature's underlying logic. You can see this in the natural world if you know where to look. Dripping faucets sometimes fall into chaotic rhythms, each droplet's timing unpredictable but statistically consistent. The population cycles of predators and prey can oscillate irregularly, yet hover within certain bounds. Even the patterns of the human heartbeat can wander into chaos and back again as the body adjusts to stress or rest. In each case, the system explores a vast landscape of behaviour, but it never escapes its invisible borders. Strange attractors remind us that chaos has memory. Each new state depends on the one before, connected by cause and effect. The trajectory may twist and fold endlessly, but it never loses continuity. This is what makes chaotic systems different from randomness. Randomness has no memory, while chaos remembers everything. It carries the imprint of its past, even as it becomes impossible to predict its future. If you've ever watched clouds form and dissolve or waves crash on a shore, you've witnessed this kind of order in motion. Every ripple is unique, yet all obey the same patterns of fluid dynamics. The details shift endlessly, but the overall form persists. That balance between freedom and constraint, between law and unpredictability, gives the world much of its natural texture and beauty. Scientists studying chaos have learned that it is not an anomaly, it's the norm. Many systems in nature, from weather to economies, from ecosystems to neural activity, operate in this sensitive, non-linear regime. Far from being a nuisance, chaos provides flexibility and adaptability. It allows systems to explore many possibilities without losing coherence. Even the human brain thrives in this middle ground, balance between rigid order and pure randomness. There's something poetic in that idea. Our thoughts, moods, and actions, seemingly unpredictable, may trace their own strange attractors, looping through states of mind that never repeat, yet remain bounded by who we are. Life itself could be seen as a chaotic system, guided by laws but shaped by sensitivity to every small influence. A chance encounter, a brief delay, a subtle change can alter the path dramatically. Yet the arc of existence still follows an invisible rhythm. Chaos theory invites a gentle kind of awe. It reminds us that unpredictability does not mean meaninglessness. Even when systems seem to behave wildly, they still carry the fingerprint of structure. The hidden geometry of strange attractors shows that the universe is both wilder and more ordered than we might expect. It is unpredictable, but not unfathomable. So when you look at a storm rolling across the horizon, or the flickering dance of candlelight, remember this. What seems chaotic is often just complexity in motion. Beneath every swirl and eddy lies an unseen pattern, folding and unfolding, shaping the flow. Chaos doesn't wander aimlessly. It dances within invisible boundaries. It remembers where it has been, even as it refuses to tell you where it will go next. If you look closely at the world, you might notice something strange. The closer you look, the more the same shapes seem to repeat themselves. A tree branch looks like a miniature version of the whole tree. The veins in a leaf resemble the branches they grow from. The cracks in dry mud look like river deltas seen from space. Nature, it seems, has a favourite design philosophy: copy and scale. This repeating order across size is the essence of fractals, one of the most elegant ideas ever uncovered about the geometry of the natural world. The word fractal comes from the Latin fractus, meaning broken or fractured, but it really describes something endlessly detailed, shapes that look similar no matter how closely you zoom in. Unlike the perfect circles and triangles of classical geometry, fractals are rough, irregular, and alive with structure. They blur the boundaries between art and mathematics, between chaos and order, and once you start noticing them, they appear everywhere. Take a coastline, for example. From far away it might look like a simple curve along the edge of a continent, but as you move closer, bays become peninsulas, and peninsulas become tiny inlets. Zoom in further, and you find even smaller versions. Rocky coves, miniature islands, and grains of sand whose edges still carry the same uneven outline. There's no single correct length for a coastline, because its details repeat endlessly at smaller and smaller scales. Measuring it depends on how close you're willing to look. This is known as the coastline paradox. The more precisely you measure, the longer it gets. Nature refuses to be smoothed down into simple geometry. Fractals are not just curiosities, they're practical solutions. The branching structure of trees, for example, follows fractal principles that allow them to capture sunlight efficiently and transport water from roots to leaves. Each branch splits into smaller branches, and those into smaller ones still, maintaining a pattern that repeats at multiple scales. The same design appears in rivers flowing into tributaries, in the bronchi of your lungs, and in the networks of neurons inside your brain. Fractals are nature's way of distributing things, light, water, air, and information, with remarkable efficiency. Lightning provides another perfect example. When a bolt strikes, it doesn't travel in a straight line. Instead, it forks, splits, and branches again and again, each division echoing the shape of the whole. This pattern isn't random. It's governed by how electricity searches for the path of least resistance through the air. The result is a self-similar design, each smaller bolt a reflection of the main one, scaled down like a recursive mirror. Snowflakes, too, are fractal marvels. Their delicate arms repeat crystalline motifs that radiate outward, each level of detail mimicking the last. Though no two snowflakes are identical, each one is built on the same repeating rule of growth, guided by the microscopic physics of freezing water. The mathematician Benoit Mandelbrot, who coined the term fractal in the 1970s, realized that these shapes weren't exceptions, they were the rule. The natural world, he observed, doesn't build with Euclid's perfect lines and circles. It builds with recursion, iteration, and feedback. When you repeat simple processes over and over, allowing each step to influence the next, fractals naturally appear. Clouds, mountains, coastlines, and ferns all share this recursive signature. They are products of simple rules multiplied through scale. One of the simplest mathematical fractals, the Koch snowflake, begins with a triangle. On each side you add a smaller triangle, then smaller ones on each new edge, continuing forever. With each step, the shape becomes more intricate, yet it always retains its overall form. The idea may sound abstract, but nature uses the same trick: growth through repetition. Branching corals, frost patterns, and even the structure of galaxies follow fractal principles, producing complexity from repetition rather than design. This self-similarity also makes fractals remarkably efficient. A tree's fractal network of branches ensures that every leaf can access sunlight and air with minimal material. Your lungs use the same strategy. 23 levels of branching tubes lead to hundreds of millions of tiny air sacs, maximizing surface area for gas exchange. If your lungs were unfolded and spread flat, their internal surface would cover the area of a tennis court, and yet they fit neatly inside your chest because fractal geometry allows vast surface area to be packed into small volume. The same rule applies to blood vessels, river systems, and root networks, nature's version of perfect engineering. Fractals even appear in places where we might least expect them, in the fluctuations of the stock market, in patterns of heartbeat intervals, and in the clustering of galaxies across the cosmos. These are systems where feedback loops generate structure over time, creating patterns that repeat in statistical, if not exact, ways. When physicists study the large-scale distribution of matter in the universe, they find a web-like arrangement of galaxies and filaments that looks astonishingly fractal. The same kind of structure found in a leaf vein seems to echo across billions of light years. What's remarkable about fractals is that they blur the line between randomness and order. They have both, randomness in the small details, order in the overall pattern. This balance gives them a lifelike quality, something too irregular to be designed yet too consistent to be accidental. Artists have long recognized this appeal. The swirling forms of clouds in landscape paintings, the branching in Japanese bonsai, even the algorithms behind computer-generated landscapes in films all rely on fractal mathematics to capture the organic complexity of the real world. But fractals are not only about beauty, they're about understanding. Before Mandelbrot's work, many natural phenomena seemed too messy to describe mathematically. Classical geometry could not handle the irregular shapes of mountains or the delicate lacework of ferns. Fractals provided a new language, one that could describe roughness itself. Instead of seeing irregularity as a flaw, mathematicians began to see it as structure on a different level. It wasn't disorder, it was detail. There is also something deeply comforting about fractals once you see them for what they are. They reveal that complexity doesn't require complexity in its rules. The same simple instructions, branch, divide, repeat, can generate endless diversity. That principle applies beyond mathematics. It explains why snowflakes differ, yet all look like snowflakes, why forests differ, yet all look like forests, and why galaxies differ, yet all spiral in familiar forms. The universe doesn't invent new blueprints for every creation. It refines and reuses its favourites. If you've ever walked through a forest and noticed how small ferns mirror the shape of larger ones, or how rivers mimic the branching of trees above them, you've already seen the signature of fractals. They're reminders that nature's creativity doesn't come from randomness alone. It comes from the repetition of simple patterns across scale. From the smallest crystal to the largest galaxy cluster, the same geometry whispers through everything. Fractals teach us that the universe is both infinite in detail and economical in design. Every scale tells the same story, only in a different voice. A coastline, a lightning bolt, a snowflake, a galaxy. They all speak the same mathematical language, one of iteration, feedback and flow. If you zoom far enough into the world around you, down past cells and molecules to the realm of atoms themselves, something beautiful begins to happen. Even here, among particles too small to see, there is cooperation. Atoms find partners, molecules gather in groups, and order begins to appear. It is not planned or forced. It happens naturally, driven by the quiet tug of energy and the subtle mathematics of attraction. This is self-assembly, the art of matter organizing itself. At first it might seem miraculous that anything so tiny and restless could arrange into something stable. Molecules are constantly jostling, colliding and spinning in the endless dance of thermal motion. And yet, from that chaos, intricate order arises. Crystals form with perfect symmetry, membranes curve into spheres, and viruses build flawless shells from identical pieces. All of it happens spontaneously, as if the universe itself were tidying up at the molecular scale. Even atoms seem to prefer company. To understand how this works, think of energy as a kind of landscape. Every possible arrangement of molecules sits somewhere on that landscape. High hills represent unstable configurations, arrangements that require energy to maintain, while valleys represent stability. When left alone, systems tend to roll downhill toward lower energy, finding the shapes and structures that require the least effort to sustain. This search for balance is the guiding principle of chemistry. Molecules don't need instructions. They just follow the contours of this invisible terrain until they settle somewhere comfortable. Take salt, for example. When sodium and chlorine atoms meet, they arrange themselves into a repeating cubic pattern, each atom surrounded by its opposite charge. They don't do this because they have a plan, but because that arrangement minimizes energy. Each positive ion nestles next to negatives in a perfect balance of attraction and repulsion. The result is a crystal, a geometric expression of stability, born from countless microscopic negotiations. Crystals are among the simplest examples of self-assembly, but the concept reaches far beyond the mineral world. In the watery environment of living cells, molecules called lipids spontaneously arrange themselves into thin layers. Each lipid has a head that loves water and a tail that hates it. When placed in water, they gather into double layers with their tails tucked safely away inside, creating a barrier between the watery outside and the watery inside. Without any designer or blueprint, the first biological membranes assemble themselves. From such humble chemistry, the containers for life are formed. This same principle builds much of the microscopic world. When lipids close in on themselves, they form tiny spheres called vesicles. These structures can trap molecules inside, offering both protection and the chance for reactions to occur in isolation. The shape they take, often a perfect sphere, is not random but a solution to an energy problem. A sphere has the smallest possible surface area for a given volume, minimizing the tension in the membrane. It's as though the molecules are whispering, "Let's stay close, and let's do it efficiently." Even more astonishing are viruses, those intricate particles that straddle the line between life and chemistry. A virus consists of a core of genetic material, enclosed in a protective protein shell called a capsid. What's remarkable is that this shell can assemble itself without any external help. Dozens or hundreds of identical protein subunits spontaneously arrange into geometric patterns, often icosahedrons or spirals, simply because those arrangements represent energy minima. The result is a structure as precise as any man-made nanomachine, built entirely through the quiet cooperation of molecules following the path of least energy. Self-assembly doesn't require consciousness or guidance, only the laws of physics and the constant shuffle of motion. Molecules move randomly, but their interactions are not random. They're governed by forces, electrical, magnetic, hydrophobic and van der Waals, that nudge them towards certain configurations. The randomness provides exploration. The forces provide selection. Together, they allow matter to search for patterns that work. Chemists describe this process using the language of energy landscapes. Imagine a ball rolling over a hilly terrain. If the hills are steep and the valleys deep, the ball will quickly settle in one of the lowest spots, a stable structure. But if the landscape is rough, with many small dips and peaks, the ball may get trapped in a local valley that isn't the deepest possible one. Molecules behave the same way, sometimes settling into good enough arrangements that persist for long times, even if better ones exist. That is why nature can produce both order and imperfection side by side. Perfect crystals alongside glass, symmetrical viruses alongside slightly flawed ones. In the laboratory, scientists have learned to harness self-assembly to create new materials. By designing molecules with specific shapes and charges, they can encourage them to assemble into predictable patterns, nanowires, layers, or cages that can trap other molecules inside. These principles are already being used in medicine, where self-assembling nanoparticles deliver drugs directly to cells, and in electronics, where tiny components organize themselves into circuits thinner than a strand of hair. The dream is to let matter build its own machines, following the same patient rules that the universe has used since the beginning. What's striking is how little control is actually needed. Provide the right ingredients, and order appears almost inevitably. Snowflakes grow into intricate six-fold symmetry because of the way water molecules lock together as they freeze. Soap bubbles form perfect spheres because surface tension distributes forces evenly. Proteins fold into exact shapes because of the balance between hydrophobic and hydrophilic regions along their chains. These are not miracles of design, but inevitabilities of physics. Given energy, motion and time, matter finds harmony. Self-assembly also blurs the line between the living and the non-living. The same forces that shape a snowflake also shape the membranes of cells. The same drive toward lower energy that forms crystals also folds DNA into its spiraling double helix. Life may seem unique in its complexity, but it builds on universal principles. The difference is scale, not kind. Chemistry doesn't stop being creative once biology begins. It simply learns new ways to cooperate. There is a serene beauty in realizing that the universe does not always need intervention to organize itself. Patterns and structures arise because that is what matter does when given the freedom to move and interact. From the hexagonal lattice of a honeycomb to the molecular elegance of a virus, self-assembly shows that order is not something imposed upon the world. It is something that emerges quietly from within it. At the smallest scales, even atoms seem to prefer company. They reach out, form bonds, and find balance in collective shapes. Each connection releases a little energy. Each pattern lowers tension until chaos gives way to calm. And though we often think of chemistry as a science of reactions and explosions, much of its true magic lies in stillness, in the moment when molecules stop searching because they found where they belong. In that gentle settling, the foundations of the visible world are built. Rocks, shells, snowflakes, and cells. All are the result of matter finding comfort. In the soft murmur of attraction and the patient pull of energy, the universe builds itself, one molecule at a time in patterns both fragile and eternal. Life began not with a spark of magic, but with a slow and patient chemistry lesson. Long before oceans shimmered with creatures or air was filled with breath, the Earth was a restless experiment. Volcanoes exhaled gases, lightning stitched across the skies, and rain carried minerals and molecules into pooling waters. These were the planet's first laboratories, warm, chaotic, and full of potential. Out of this chemical noise, something extraordinary began to happen. Molecules started to cooperate. At its heart, life is chemistry that learned to sustain itself. Ordinary chemical reactions happen all the time. They flash, fizzle, and fade. But life depends on reactions that don't end, that feed themselves and keep cycling. Somewhere in the ancient world, small sets of molecules discovered this trick. They formed autocatalytic cycles, reaction loops where the products of one step became the ingredients for the next. Once such a loop begins, it can grow stronger, pulling in energy and resources to maintain its rhythm. It's chemistry that, in a sense, learns to breathe. Imagine a group of molecules floating in a tide pool, reacting by chance. Most reactions create byproducts that drift away, but occasionally one of those byproducts helps the reaction start again, perhaps by speeding it up or stabilizing it. Once that happens, the molecules begin to support each other, forming a self-sustaining cycle. The cycle doesn't think or plan, it simply persists because it can. Over time, these loops became more intricate, connecting with others, forming networks of reactions that grew increasingly resistant to disruption. But chemistry alone wasn't enough. These fragile cycles needed boundaries, some way to protect themselves from the chaos outside. That's where membranes entered the story. Fatty molecules, or lipids, are naturally inclined to form spheres in water, hiding their oily tails inside and exposing their water-loving heads to the outside. When these membranes enclosed an autocatalytic network, something astonishing happened. The reaction was no longer adrift, it was contained. Inside the tiny bubble, energy could circulate, materials could flow, and the system could grow. These primitive bubbles were the ancestors of cells, microscopic sanctuaries of order surrounded by the sea of entropy. Inside these early membranes, chemistry started to take on the properties we now associate with life. Energy flowed through them, not chaotically, but along structured pathways. Molecules began to specialize, some storing energy, others speeding up reactions, others providing stability. Feedback loops emerged. If one molecule accumulated too much, it slowed its own production. If another became scarce, reactions shifted to make more of it. These self-correcting processes are still the heartbeat of every living cell today. Life learned to balance itself, not perfectly, but well enough to endure. The next great leap came when certain molecules learned to carry information. Among the vast assortment of compounds swirling through early Earth, some could store their structure in a repeating chain, much like a necklace of chemical beads. These chains could make imperfect copies of themselves, preserving useful arrangements while allowing variation. Over countless generations, this molecular memory began to evolve. Those sequences that helped the chemical network survive were copied more often. The first whispers of natural selection had arrived, long before DNA, or even the first true cell. Many scientists suspect that RNA, a close chemical cousin of DNA, played a starring role in this period. RNA can both store information and catalyze reactions, meaning it could act as both instruction and machinery. It's a bit like having a tool that can also make copies of itself. In the bubbling chemistry of ancient Earth, such molecules could have formed naturally, copying imperfectly but persistently. And with every copy came the possibility of improvement. Random changes that made replication faster or more stable spread through the molecular population. The line between chemistry and biology began to blur. Energy, information, and boundaries. Those three ingredients formed the recipe for life. Energy provided motion and drive. Information allowed continuity and adaptation. Boundaries gave structure and identity. Together, they transformed a chaotic soup of reactions into something capable of growth, repair, and reproduction. Once these systems gained a foothold, they could spread, dividing and sharing their chemistry with new environments. Over time, the feedback between structure and survival turned simple molecules into something astonishingly resilient: cells. Cells became nature's new playgrounds for innovation. Within their membranes, networks of reactions became increasingly sophisticated. Some learned to harness sunlight, capturing photons and converting their energy into chemical fuel. Others learned to consume neighboring molecules, breaking them down for power. As these tiny systems diversified, competition began, not as a war but as a quiet sorting process. Those combinations that maintained stability thrived. Those that couldn't vanished. Slowly, selection turned chemistry into evolution. The world began to change. The oceans filled with microscopic architects of order, each one balancing the chaos of their surroundings with the structured dance inside their membranes. Some formed communities, exchanging molecules and sharing energy. Others drifted alone, living brief but productive lives. From these humble origins, the long story of biology unfolded, from single cells to multicellular organisms, from seaweed to starfish, and eventually to us. But at its foundation, life remained what it had always been, a self-sustaining flow of energy and information within a boundary. When viewed from this perspective, life feels less like an exception to the universe's rules and more like their natural consequence. The same forces that shape crystals and clouds also shape living systems. The difference is persistence, life's ability to hold its structure while change flows through it. Every cell in your body is a pattern kept alive by constant renewal. Molecules enter and leave, but the organization remains, as if life is a flame sustained by fuel rather than an object fixed in time. This persistence comes from feedback. Life is full of loops, enzymes that activate or inhibit others, genes that regulate their own expression, membranes that control what enters and exits. These loops act like the rudders of a ship, steering chaos into stability. They don't eliminate randomness, they use it. Mutations, fluctuations, and chance encounters become opportunities for adaptation. Life survives not by resisting change, but by learning to ride it. The transformation from chemistry to biology was not sudden. There was no single spark, no instant when the inanimate became alive. It was a slow dawn, spread across millions of years, with countless failed experiments along the way. But somewhere in that long twilight, the balance tipped. Feedback turned fragility into resilience, replication turned chance into inheritance, and boundaries turned chemistry into identity. When you trace life back to its beginnings, it becomes clear that the essence of living things is not perfection or permanence, but the ability to maintain form through constant motion. The same molecules that built the first cells still flow through your veins and cycle through the oceans. Life is not a substance, it's a process, a self-renewing pattern written in chemistry and sustained by sunlight. Life is chaos that learned to keep its shape. It endures not by escaping disorder, but by organizing it, weaving randomness into rhythm. The same quiet laws that once guided atoms into crystals and lipids into membranes now guide cells into beings capable of thought, memory and wonder. From the restless chemistry of early Earth came the first whispers of order that would one day open eyes, look back, and try to understand how it all began. When you look at the world of living things, it's hard not to be amazed by how beautifully structured everything is. A fern unrolls with perfect geometry, a shell curls in a precise spiral, and the veins of a leaf spread like a carefully drawn map. Yet none of these designs are drawn by hand, nor are they planned from above. They emerge from the simplest of instructions, followed faithfully by cells that respond to local cues. The process by which living organisms shape themselves, by turning chemistry into architecture, is called morphogenesis. It is nature's quiet art of building form from within. At the beginning, every multicellular organism starts as a single cell, a tiny bubble of potential. Through division, it multiplies into a community of identical copies. At first, there's no hint of what they will become, no sign of wings, branches, or bones. Then, slowly, differences begin to appear. Certain cells receive one signal, others sense another. Some start to stretch, some to fold, some to migrate. These local behaviors, multiplied millions of times over, create the organized structures we recognize as bodies. The magic lies not in a single master plan, but in the way each part communicates with its neighbors. Cells use chemical gradients to know where they are. Imagine a landscape covered in invisible hills and valleys of concentration, molecules diffusing from one region to another. A cell that detects more of one chemical might decide to become a nerve cell. Another, sensing less, might become muscle. These gradients act as coordinates, guiding development without any need for a central command. In embryos, such gradients are often set up by just a few genes, yet they define where heads, tails, and limbs will grow. A cell doesn't need a map of the whole body. It only needs to read the chemical whispers in its immediate neighborhood. Once those early decisions are made, feedback takes over. Cells don't simply follow orders, they talk back. When one cell changes its fate, it can influence others nearby, strengthening or suppressing certain signals. This feedback ensures that growth remains balanced, that a limb stops elongating once it reaches the right proportions, or that a leaf's veins connect neatly without overgrowing. It's a living conversation, full of trial and correction. Development isn't a mechanical assembly line, It's a negotiation between billions of tiny participants, all improvising within shared rules. Gene networks act as the language of this communication. Inside every cell, genes switch on and off in response to chemical and mechanical cues, forming circuits of regulation. These genetic switches interact much like electrical networks. One gene activates another, which inhibits a third, which loops back to the first. The result is a dynamic pattern that can create stripes, spots, or waves of activity. Alan Turing's theory of reaction diffusion, first imagined for chemicals, finds its biological echo here. The same logic that paints spots on a leopard's coat also helps lay out the repeating segments of an insect or the radial arms of a starfish. Nature, it seems, loves to recycle a good idea. The shapes that emerge from these interactions are astonishingly diverse. In plants, growth follows gradients of hormones like auxin, which tell cells when to divide and where to bend. The veins of a leaf form as rivers of auxin flow outward, branching naturally as they go. Each new branch slightly alters the gradient, guiding the next one in turn. What looks like delicate artistry is really self-organization at work. Order growing organically out of feedback and flow. In animals, similar principles sculpt the body from a uniform sheet of cells. Limbs, for instance, begin as small buds. Chemical gradients tell cells which side is up, which side is down, and where the tips will grow. Genes then switch on in carefully timed patterns, carving out bones, muscles, and nerves. One set of signals ensures symmetry between left and right, while others allow variation, so that fingers form separately rather than merging into a fin. These processes are so reliable that even if part of an embryo is damaged, development often finds a way to correct itself, like an orchestra seamlessly recovering from a missed note. The coral reefs that dot the oceans are built using the same subtle rules. Each coral polyp follows local cues, secreting calcium carbonate in response to its neighbours. Over time, millions of them build structures that seem architectural in their precision, domes, spirals, and branching antlers. Yet no single polyp has the blueprint. Each one simply responds to its local environment, light, flow, and contact. The reef's beauty emerges collectively, not deliberately. Seashells grow in much the same way. Along the edge of a mollusk's shell, cells deposit minerals in rhythmic patterns, guided by feedback between chemistry and growth. Changes in nutrient flow or temperature alter the pattern slightly, creating stripes, ripples, or spirals. The graceful curve of a nautilus shell, for example, follows a logarithmic spiral, a mathematical form that maintains the same shape as it grows. The animal doesn't need to calculate it. The geometry arises naturally from the balance of forces and rates. Growth itself writes the formula. Even in creatures as complex as humans, the same rules govern the sculpting of form. The folds of the brain, the ridges of fingerprints, and the branching of blood vessels all emerge from mechanical and chemical feedback. When tissue grows faster in one region than another, it buckles and folds, creating curves that increase surface area. When oxygen becomes scarce, cells release signals that attract new blood vessels, branching toward the deficit. Each structure is a response to local conditions, not a predetermined design. Yet, through these interactions, a coherent whole emerges, a body capable of movement, thought, and awareness. What's remarkable is how robust these processes are. Development tolerates imperfections, adapting gracefully when conditions change. If a gradient shifts slightly, cells recalibrate. If one pathway is blocked, another compensates. Life builds itself not by strict control, but by flexibility. It is this adaptability that allows evolution to explore new shapes over time. A small mutation in a gene network can alter a gradient or a feedback loop, leading to a subtle change in form, a longer limb, a new pattern of veins, a shell that curls differently. From such small adjustments, the diversity of life unfolds. Morphogenesis reminds us that complexity doesn't require complexity in its rules. The same basic principles, local interaction, feedback and energy flow, create everything from a blade of grass to a human hand. Each organism is an echo of these universal patterns, shaped by chemistry but refined by evolution's patient hand. And because the process is decentralized, it's resilient. The body, in all its delicacy, is built from chaos that knows how to self-correct. There's something deeply peaceful in this realization. Every living shape, from the spiral of coral to the curl of a fern, is the result of matter finding its balance. Growth, for all its precision, is simply the expression of cells obeying local truths. Divide here, stop there, follow the gradient, respond to your neighbour. From those simple rules, a forest blooms, a body forms, and the world fills with pattern. Life's architecture is not dictated from above, but composed from within, like music rising naturally from harmony. Each note, each cell responds to the others until the melody of form emerges. The laws of physics may set the rhythm, but biology writes the tune. There are few sights in nature more hypnotic than a murmuration of starlings. Thousands of birds sweep and twist across the sky, as if guided by a single thought, the whole flock flowing like smoke through air. Yet there's no leader issuing commands, no conductor waving invisible wings. Each bird simply follows a handful of simple rules. Keep your distance, match your speed, move toward your neighbours, and from that simplicity, the grand choreography emerges. No leader, no plan, just beautifully organised confusion. This phenomenon, where order arises from the collective behaviour of many individuals, is known as emergence. It's one of nature's favourite tricks. From schools of fish to traffic on highways, from colonies of ants to human crowds, the same principle applies. When enough agents follow local rules, global patterns appear. Each individual knows almost nothing about the whole, yet together they generate a structure that feels intentional, even intelligent. For the starlings, the benefit is safety and coordination. When a hawk dives toward the flock, the disturbance ripples through it like a wave through water. Each bird only reacts to its immediate neighbours, yet the information spreads instantly across thousands. The flock turns, folds, and reforms without collision. It's a kind of living fluid, one that responds faster than any single bird could manage on its own. Scientists studying these murmurations have found that each starling tracks about 7 of its nearest companions. Not too few to lose connection, not too many to cause chaos. That balance creates a network both flexible and coherent, where change travels at the speed of sight. Fish schools work in much the same way, though their world is liquid instead of air. A shimmering shoal of sardines or anchovies behaves as one massive organism, splitting and merging as predators approach. The underlying rules are simple: swim in the same direction, stay close and avoid collisions. These local interactions create global coherence. The result is protection through confusion. A predator trying to single out one fish is dazzled by the collective motion of thousands. The school itself becomes a moving, shifting body with a single fluid identity. Even insects, creatures without large brains or complex social planning, show this kind of emergent order. Ants build vast colonies and intricate trail networks without any master architect. Each ant follows chemical cues, depositing tiny pheromone trails that guide others. When a food source is found, more ants reinforce that path, and soon a highway forms between nest and meal. If a shortcut appears, the system adjusts automatically, strengthening the new path. The result is an intelligent network built entirely from feedback and repetition. A single ant might be clumsy, but together the colony behaves as if it thinks. Humans too are participants in this dance of collective behaviour. though we don't always notice it. Anyone who has been caught in dense foot traffic at a concert, a festival, or a busy city street has experienced how crowds flow almost organically. Individuals adjust their pace and direction based on those around them, and lanes of movement appear spontaneously. The crowd self-organizes, splitting and merging like a liquid. There's no one directing, but there's still a sense of order. If you've ever tried to go against that flow, you'll quickly learn that the crowd always wins. The same principles apply on roads. Traffic jams, those modern swarms of frustration, can arise from nothing more than a momentary hesitation. One driver tapping the brakes a little too hard, another reacting slightly late. The disturbance travels backward through the line of cars like a shock wave, slowing vehicles miles behind the original cause. It's a human-scale version of a flock's ripple, but less graceful and far less entertaining. Interestingly, computer simulations have shown that if every driver simply maintained a steady distance and smooth acceleration, following rules as simple as starlings do, traffic would flow almost perfectly. Apparently birds are better at driving than we are. What makes Emergent so fascinating is that it reveals intelligence without intention. There's no central control, no overseer coordinating the parts, yet the system behaves in a way that seems guided. Physicists describe this as self-organization, when order arises spontaneously out of local interactions and feedback. It's the same kind of process that builds snowflakes, galaxies, and cells. The difference here is that the agents, birds, fish, people, are moving, sensing, and adapting in real time. Their constant reactions create a feedback loop that keeps the group stable but flexible, ordered yet dynamic. The beauty of collective order lies in its adaptability. A murmuration can shift direction in an instant without breaking apart. A school of fish can fracture and rejoin seamlessly. A crowd can flow around an obstacle as if anticipating it. These systems are resilient because they have no single point of failure. Remove one bird, one fish, one person, and the pattern continues. The intelligence is distributed across the group, a kind of wisdom shared among many rather than stored in one. This kind of emergent behavior has inspired scientists and engineers in surprising ways. Modern algorithms for controlling drones, robots, and even search patterns for disaster recovery all borrow from swarm intelligence. By programming machines with a few simple local rules, much like starlings or ants, researchers can create systems that explore, communicate, and adapt on their own. The power lies in the simplicity. When every agent follows basic principles of alignment, avoidance, and attraction, complex order naturally unfolds. In nature, these same principles extend far beyond animals. Slime molds, for instance, are single-celled organisms that, when food is scarce, merge into a collective superorganism. Together they form branching networks that efficiently connect food sources, often finding routes as optimal as those designed by human engineers. They solve problems not by thought, but by physical interaction, by being part of a self-adjusting pattern. If you could step back far enough, you might see this principle everywhere. Forests function like swarms of trees, each one responding to light, water, and neighbours through underground fungal networks. Economies behave like vast ecosystems, built on countless local exchanges that generate global patterns. Even the neurons in your brain, billions of them firing and interacting, create the emergent phenomenon you call thought. You are, in a way, your own murmuration. There's a quiet humility in realizing that much of the world's elegance doesn't come from control, but from cooperation. The starlings don't need a leader to create art in motion. The fish don't need instructions to swim as one. Complexity emerges because simplicity interacts. Each participant contributes only a fragment of information, but together they form something greater than the sum of their parts. If you watch a flock long enough, you begin to sense a kind of serenity in the chaos, a reminder that beauty doesn't always require a plan. The universe itself may follow similar rules, with galaxies, stars, and atoms all behaving according to simple laws that together produce endless variation. From the cosmic to the communal, order finds a way to emerge from the conversation between parts. So the next time you see a cloud of starlings twisting above a sunset or a crowd flowing effortlessly through a busy street, think of how little each individual knows and how much the group accomplishes. It's not command that makes the pattern work, but connection, the quiet, constant adjustment of one being to another. No leader, no plan, just beautifully organized confusion. And within that confusion lies one of nature's most profound truths. Order does not always need to be imposed. Sometimes it simply appears when enough things learn how to listen. The natural world is not a hierarchy, but a conversation, a constant exchange of energy, matter, and motion. Every forest, reef, or meadow is a web of interdependence, each part quietly influencing the rest. We call these systems ecosystems, but that word hardly captures their living texture. They are not static arrangements of species or habitats, but dynamic processes in motion, a choreography of feeding, growing, decaying, and renewing. At first glance, they may look chaotic, yet beneath the surface lies a fragile equilibrium. Life endures not by perfection, but by graceful imbalance. An ecosystem works much like a network of feedback loops. Every organism participates in flows of energy and nutrients, taking from one source and returning to another. Plants capture sunlight and carbon dioxide to build themselves from air and water. Herbivores eat the plants, carnivores eat the herbivores, and decomposers break down what remains, returning nutrients to the soil for the cycle to begin again. It's an elegant exchange that never really stops, the rhythm of existence in steady circulation. Yet it's not a closed system. Weather, sunlight, and geology all interfere and adapt, and through it all, life adjusts, compensating for shifts and surprises. In a healthy ecosystem, feedback keeps everything in check. When one population grows too large, its success eventually limits itself. Predators increase, resources decline, or disease spreads. When it shrinks too far, recovery begins as competitors ease and the environment replenishes. These feedbacks don't make ecosystems stable in the sense of stillness. They make them stable through movement. Like a tightrope walker, balance is maintained not by freezing in place, but by constantly correcting. Resilience is the secret ingredient that allows ecosystems to withstand disturbance. Forests burn, rivers flood, and coral reefs bleach, yet life often finds a way back. Resilience doesn't mean nothing changes. It means that after change, the system can still find a way to function. Diversity plays a key role in this. When there are many species filling overlapping roles, the loss of one doesn't collapse the whole web. Different players can step in, absorbing the shock. A grassland with many types of grasses and grazers, for example, can recover from drought more easily than one dominated by a single kind. Diversity is nature's insurance policy against uncertainty. This principle shows up at every scale. A tropical rainforest hums with redundancy, hundreds of pollinators for each flower, multiple decomposers for each leaf. That overlap may seem wasteful, but it's what keeps the system resilient. If a disease wipes out one pollinator, others continue the work. If a storm fells ancient trees, sunlight reaches the forest floor and dormant seeds awaken. Change is not a threat, it's part of the design. The forest's complexity is its shield. Competition and cooperation weave together in this grand balancing act. Predators hunt prey, but their presence keeps populations healthy by removing the weak and preventing overgrowth. Plants compete fiercely for sunlight, Yet through their roots and fungal networks, they also share nutrients and warning signals. Coral reefs teem with rivalry. Fish defending territories, corals jostling for space, and yet the entire reef is built upon cooperation between coral animals and the microscopic algae that live within their tissues. Those algae feed the coral through photosynthesis, while the coral provides protection and minerals in return. The partnership creates a structure so vast and intricate it can be seen from space. This blend of conflict and collaboration is what keeps ecosystems dynamic. Too much competition leads to collapse. Too much cooperation leads to stagnation. The balance between the two is always shifting, always adjusting to circumstance. In a sense, ecosystems behave like living arguments, full of tension and compromise, but productive because of it. Even the soil beneath our feet is alive with negotiation. A single handful can contain more microorganisms than there are humans on Earth. Bacteria, fungi, and microscopic animals trade nutrients and energy through vast underground networks. Some plants secrete chemicals to attract beneficial microbes. Others defend themselves against invaders. The result is a self-regulating system, where waste becomes resource and decay becomes renewal. Life's tendency to recycle itself is perhaps its most elegant feature. Nothing is ever truly lost, only transformed. On larger scales, these patterns continue. The migration of animals redistributes nutrients across continents. Whales fertilize plankton with the iron they bring up from deep dives. Forests influence rainfall by releasing water vapor into the air. Even deserts and oceans, seemingly separate worlds, are connected by the dust that blows between them. The entire planet behaves as one vast interlinked ecosystem, a balance maintained through countless local interactions. Humans, of course, are part of this network, though we often behave as if we stand apart from it. Our cities, farms, and industries tap into these natural cycles, altering their flow. When balance is lost, when we remove too much diversity, extract too many resources, or disrupt feedback loops, ecosystems lose their resilience. They can shift into new states, often less capable of supporting the life that once thrived there. A forest cleared beyond a certain point might not grow back. A coral reef bleached too often may turn to rubble. The lesson isn't that nature is fragile, but that balance has limits. Push too hard in one direction, and the self-correction fails. Yet ecosystems are also forgiving. Restoration efforts show that if the pressures ease, recovery begins almost immediately. Forests regrow, wetlands refill, fish return to rivers. Life's persistence is astonishing, an unbroken chain of adaptation billions of years long. Even when entire species vanish, the pattern of life continues, reorganizing around what remains. The web never stops weaving itself back together. What's remarkable about this constant motion is that no one is in charge. There's no grand conductor directing the forest or the reef. The order emerges naturally through feedback and flow. Each organism responds to its local conditions, and out of those countless small responses comes planetary scale stability. It's a humbling thought that the world's balance is maintained not by control, but by interaction. If ecosystems were perfectly balanced, they would never change, and life would never evolve. But the world thrives precisely because it is always slightly off balance, always adapting to new circumstances. It's that gentle tilt away from equilibrium that keeps things alive. A storm opens space for new growth. A wildfire returns minerals to the soil. Even decay itself is a form of renewal. Life, in all its forms, depends on constant motion, a dance between creation and destruction, competition and care. So when you walk through a forest or stand on a shoreline, you're witnessing this endless balancing act. Every rustling leaf, every passing breeze, every drop of water sliding down a rock, is part of a conversation millions of years in the making. The system endures not because it is perfect, but because it knows how to bend. Life endures not by perfection, but by graceful imbalance. The secret to stability lies not in stopping change, but in learning to flow with it, a lesson the Earth has been practicing for billions of years, and one we're still learning how to follow. If you've ever built a sandcastle or poured dry sand into a pile, you've seen a quiet law of nature at work. At first, the grains slide smoothly down the slope, each new one finding a place to rest. But as the pile grows taller, something changes. The slope steepens until a single added grain can send a small cascade tumbling down the side. The pile doesn't collapse entirely, it just readjusts, finding a new balance. Add another grain, and perhaps nothing happens. Add one more, and the slope shifts again. This dance between stillness and motion, between order and collapse, is an example of self-organized criticality. The term sounds intimidating, but the concept is beautifully simple. Many systems in nature seem to organize themselves right on the edge between order and disorder. They're neither frozen nor chaotic, but poised in a delicate balance where small events can trigger large consequences. The sand pile is the classic illustration, but the same principle appears in forest fires, earthquakes, neural activity, and even the evolution of ecosystems. It's a kind of universal tuning, nature's preference for the point where things are just stable enough to endure, yet unstable enough to adapt. Imagine that sand pile again. Each grain added is an input of energy, a small push to the system. For a while, it absorbs those pushes without complaint, growing taller. But as it nears its critical slope, stability becomes precarious. A single grain may rest peacefully, or may start an avalanche. What's fascinating is that these avalanches follow a pattern. Most are small, a few are medium-sized, and occasionally one is large enough to reshape the entire pile. The system never stops adjusting. It never settles into a final permanent shape. Instead, it fluctuates endlessly around that critical point, always on the verge of change. Physicists first began to notice this behavior in the 1980s, when researchers Per Bak, Chao Tang, and Kurt Wiesenfeld proposed that complex systems naturally evolve towards such critical states without any external tuning, hence self-organized. They discovered that this balancing act wasn't confined to sand piles. Forests, for example, behave in much the same way. When trees grow, they accumulate fuel for fire. Small fires occasionally burn through, clearing space and releasing nutrients. If no fires occur for a long time, the forest becomes dense and unstable, until eventually a lightning strike ignites a massive blaze. The system cycles between calm and catastrophe, hovering near its own critical threshold. In a strange way, this instability is what keeps the system healthy. Frequent small disturbances prevent catastrophic ones, while total suppression of change allows tension to build until it's released all at once. It's the same in economics, ecology, and even the brain. Systems that are too rigid can't adapt. Those that are too chaotic can't sustain themselves. The sweet spot lies between, at the edge of criticality, where small fluctuations are both allowed and useful. Think about how your brain works. Billions of neurons fire and rest in a ceaseless storm of electrical activity. If everything were perfectly synchronized, you'd have no thought at all, just a steady hum of sameness. But if the firing were completely random, you'd have chaos with no coherence. The brain operates between these extremes. It's stable enough to hold memories, but flexible enough to form new ideas. Studies suggest that neural networks often hover near a critical point, where bursts of activity, sometimes called neuronal avalanches, follow the same mathematical patterns as sand piles and forest fires. This balance gives the brain its adaptability, creativity, and resilience. The same principle applies to ecosystems. A coral reef, for example, exists in a state of dynamic equilibrium. Small disturbances, storms, changes in temperature, grazing fish, constantly reshape it. If the disturbances are mild and frequent, the reef stays healthy. But if the balance tips too far, say through prolonged warming or pollution, the system crosses a threshold. Corals bleach, algae take over, and the reef as it was ceases to exist. Criticality is a narrow ridge between stability and collapse, and the living world walks it constantly. Self-organized criticality also explains why large-scale events in nature often follow power law patterns, a few big ones and many small ones. Earthquakes, volcanic eruptions, and solar flares all share this signature. They aren't predictable in detail, but their statistical distribution is remarkably consistent. Most tremors are tiny, felt by no one. A few are moderate. Rarely one is massive. The system regulates itself not through precision, but through probability. Each event, no matter how small, helps reset the balance for what comes next. This concept even applies to human systems. Financial markets, traffic networks, and social trends can all exhibit critical behavior. A few trades, a single rumor, or a shift in sentiment can ripple through a connected web of participants, triggering chain reactions. It's why markets crash, memes spread, and crowds move as one. Complex systems, whether natural or artificial, seem drawn to the same precipice between predictability and surprise. What makes this edge so special is its ability to foster adaptability. Systems far from criticality, either too ordered or too disordered, can't respond well to change. A rigid crystal shatters under pressure. A gas dissipates without form. But at criticality, the system is full of correlations, every part subtly influencing every other. It can reorganize itself when conditions shift, absorbing shocks and finding new patterns. Life itself seems to thrive in this zone, where structure and flexibility coexist. Evolution, too, operates near criticality, stable enough to preserve what works, yet always flirting with transformation. There's a poetic symmetry in how this principle appears at every scale. A sand pile in a child's hand, a rainforest spanning continents, a network of neurons firing in thought, all share the same underlying rhythm. Each builds up complexity until tension demands release, then resets, ready to begin again. Too little pressure, and nothing happens. Too much, and the system breaks. The beauty lies in the balance, the eternal teetering on the edge. If we look closely, even our own lives reflect this pattern. We seek stability, yet growth requires disruption. Comfort can turn stagnant. Change can bring renewal. Like sand piles, we grow until the next small grain, a challenge, an idea, an accident, shifts everything just enough to make a new pattern possible. We adapt, not by avoiding collapse, but by learning how to rebuild. Nature in all its forms seems to know this instinctively. Rivers meander until they find new channels. Forests burn and regrow. Galaxies swirl at the thin line between dispersal and collapse. Everywhere, systems hover around criticality. Never too rigid, never too wild. It's a way of staying alive to possibility, of remaining open to transformation without losing coherence. So the next time you watch sand sliding through your fingers, or lightning flash across a dark sky, remember that these are glimpses of the universe's balancing act. Every cascade, every spark, every tremor is part of a pattern that has no center, yet holds everything together. Time moves only one way. We wake, grow, age, and remember, but never rewind. Ice melts, smoke disperses, and a wave that crashes against the shore will never return to the shape it once had. This direction, this steady drift from order to disorder, is what physicists call time's arrow. It's the quiet pulse behind every transformation in the universe, from galaxies expanding to thoughts forming and fading in the mind. Entropy gives time its direction, and the universe its rhythm. Entropy, as you might remember, is not chaos in the dramatic sense, but rather the spreading out of energy, the slow evenness that follows every act of concentration. A hot cup of tea cools because its heat disperses into the air. A drop of ink spreads through water until its colour fills the glass. Each event unfolds in one direction only, toward equilibrium. There's no law forbidding the reverse. Heat flowing from cold to hot, ink gathering back into a droplet. But the odds are so astronomically small that for all practical purposes, it never happens. Time's arrow points forward because entropy almost always increases. And yet, within this flow toward disorder, islands of order appear. Planets, storms, crystals, living beings, thoughts. These structures seem to defy entropy, but they don't. They persist only by borrowing energy, by feeding on gradients that allow them to maintain their form for a while. A hurricane, for instance, is a temporary engine that turns heat differences between ocean and atmosphere into movement. When the gradient fades, so does the storm. Life works the same way. Organisms channel energy from their surroundings, sunlight, food, chemical bonds, to resist the pull of equilibrium. They build and rebuild themselves moment by moment, converting disorder elsewhere into order within. Even stars blazing with fusion are simply entropy machines in disguise. They turn dense hydrogen into heavier elements, releasing light and heat that spill outward through space. That energy, once absorbed by planets, becomes the fuel for every living process. Plants capture sunlight and turn it into sugars. Animals eat the plants and convert those sugars into motion. Every act of life, every heartbeat and breath is powered by a steady fall down the slope of entropy, energy spreading outward, creating temporary order along the way. The persistence of pattern in such a universe is a kind of miracle, though not a supernatural one. It's statistical. Even as entropy increases overall, local order can form as long as energy flows through. The result is a world of delicate balances. Rivers carving valleys, coral reefs growing on dead coral, forests renewing after fire. Order never lasts forever, but it can endure for astonishing stretches of time, passed from form to form like a relay of organisation. You can think of a fossil as a kind of frozen echo of that endurance. The creature it once belonged to is long gone, its soft parts dissolved, but the shape remains imprinted in stone. It's a record of a pattern that once held itself together against entropy's tide. The same is true of memory. A thought, an image, a feeling. All are patterns of electrical and chemical activity in the brain, sustained for a while by the energy of living cells. When we remember, we temporarily recreate those patterns, bringing the past into the present through structure. Memory is entropy briefly reversed by design, a spark of order replaying itself inside a moving system. Language, art and culture extend this defiance of forgetting. A poem written thousands of years ago is a pattern encoded in symbols, passed from one mind to another, reinterpreted and renewed each time it is read. Knowledge itself is an enduring pattern, kept alive not by matter but by replication. The constant reinscription of form in new media, new brains, new books. Even when civilizations crumble, fragments of their order remain, carvings, stories, equations. Each is a fossil of thought, a ripple in the flow of time that refuses to disappear completely. But endurance always comes at a cost. To preserve a pattern requires work, energy, attention and maintenance. Buildings decay if left alone. Ecosystems collapse when their energy flows are interrupted. The same holds for the mind. Memory fades when it is not revisited, and ideas wither when they are not shared. The effort to hold order against entropy is what gives time much of its poignancy. We know that everything we build will eventually erode, and yet we build anyway, turning fleeting energy into lasting form for as long as we can. Even the universe itself began in a state of low entropy, hot, dense and uniform, and has been expanding and cooling ever since. Over billions of years, its contents have arranged themselves into ever more intricate forms: galaxies, stars, planets, and life. But the long trend points toward dispersion. Stars will burn out, matter will decay, and energy will spread too thin to sustain motion. It's sometimes called the heat death of the universe, a time when entropy reaches its maximum and change effectively ceases. That distant future sounds bleak, but it is simply the natural conclusion of the same processes that made everything beautiful in the first place. The rise of order and the return to equilibrium are two verses of the same cosmic song, yet within that grand impermanence lies something deeply serene. The universe doesn't resist entropy, it uses it. The flow of energy from high to low, from concentration to diffusion, is what allows structure to exist in the first place. Every wave, every heartbeat, every orbit is a local act of balance along that gradient. Order and disorder are not enemies, they are partners in motion. Without the background drift toward equilibrium, nothing would ever happen. No growth, no decay, no life, no time at all. Perhaps that's why so many natural systems exist right on the edge of change. A forest doesn't stay still. It grows, burns, and regrows. A planet doesn't freeze or melt entirely. It cycles between states, always adjusting. Even consciousness itself relies on this dynamic tension, stable enough to form identity, fluid enough to evolve. To live, to think, to remember, is to ride that flow without ever stopping it. You could say that pattern is the universe's favourite form of resistance. Not resistance in the sense of opposition, but of persistence. It's the ability to hold shape long enough to matter, to leave an imprint before the tide takes it. The spiral of a galaxy, the whirl of a fingerprint, the rhythm of a heartbeat. Each is a way of saying that order, however temporary, is possible, and perhaps that's enough. Time's arrow keeps moving, indifferent to our desire for permanence, yet everything that exists is an echo of something that managed to organise itself, however briefly, against that current. From the molecules in your body to the stars that light the night sky, all are transient structures in the long unfolding of entropy. They will fade, as all things must, but the beauty lies in the fact that they were ever here at all. Order is never permanent, it's simply the universe catching its breath. From the first tremors of the universe to the quiet rhythm of your breathing, the story has been the same. Order and chaos are not rivals but collaborators. Chaos offers possibilities. Order selects and sustains them. Chaos stirs the stillness. Order sets the pattern. Together they have written everything we know, from starlight to seashells, from mountain ranges to mathematics, from drifting clouds to the mind that watches them drift. It began with quantum murmurs, the tiny jitters that nothingness cannot help but make. Those fluctuations were stretched across swelling space, becoming the seeds of galaxies. Gravity, patient and tireless, amplified the faintest differences into structure, drawing matter into threads and knots, weaving the cosmic web. Dark matter, invisible but undeniable, supplied the scaffolding on which everything luminous could gather. Even entropy, the great spreader of energy, allowed local islands of order to bloom wherever flows and gradients made it possible. The cosmos did not march away from chaos, it learned how to use it. We watched as matter crossed thresholds and found new rules. Water stiffening into ice, metals becoming magnetic, currents turning turbulent, patterns appearing at the edge of change. We traced the delicate logic of reaction and diffusion, where simple chemical partnerships painted stripes, spots, and spirals with no hand to guide them. We saw chaos that remembers, systems whose paths are unpredictable in detail, yet bound to elegant shapes, strange attractors that reveal an invisible geometry beneath the wildness. We followed fractals through coastlines and trees, lightning and snow, and learned how repeating rules across scale can be both efficient and beautiful. At smaller scales, molecules assembled themselves, settling into forms that balanced energy and attraction. Crystals, membranes, and the careful shells of viruses. Chemistry found rhythm in loops that fueled themselves, wrapped in protective boundaries, carrying the first whispers of information. The dawn of life was not a single spark, but a long conversation among molecules about how to persist. Feedback steadied the song, selection taught it new verses, boundaries held identity, flows delivered power, memory offered continuity. From that triad came cells, and from cells came bodies sculpted by gradients and gene networks, leaves veined by flow, limbs carved by timing, coral and seashells writing geometry with growth. We looked upward and outward again to the shared intelligence of many, learning how swarms and flocks, schools and crowds, traffic and trails all discover order through local interaction. No leader, no plan, just beautifully organized confusion that adapts swiftly and fails gracefully. We wandered through ecosystem tuned by feedback and flow, learning that resilience lives in diversity and overlap, that balance is movement, not stillness, and that life endures not by perfection, but by graceful imbalance. We came to the edge where systems prefer to live, self-organized criticality, where small nudges can shift the whole, where adaptability is born because things never quite settle. And we ended with time's arrow, the one-way tide that gives change its cadence, recognizing that patterns endure by channeling energy, renewing their shape while letting matter pass through, like water, through a net. All along, the lesson remained gentle and clear. There is no sharp boundary where the wild ends and the woven begins. The universe is both, at once. Order is the choreography of chaos, and chaos is the possibility of order. The two rise and fall together like breath. Even our lives and civilizations follow this rhythm. Cities grow as networks do, from countless simple exchanges that aggregate into culture, art, and science. Markets, ideas, and technologies drift near their own edges of change, brittle when too rigid, wasteful when too free, healthiest when they adapt. Languages evolve through use, not decree. Knowledge is a living pattern, copied and recast from mind to mind, book to book, circuit to circuit. Families, communities, and traditions are all feedback systems, correcting and renewing themselves as conditions shift. We are neither authors outside of nature nor passengers carried by it. We are participants in its ongoing negotiation between chance and form. The same principles that assembled a galaxy guide the way a thought takes shape, the way a forest regrows after a storm, the way a melody finds and keeps a listener. To see this is to soften a little. It means that unpredictability is not a failure, and impermanence is not a flaw. Patterns are not made to last forever. They are made to pass energy along, to hold shape long enough to matter, and then yield to what comes next. A spiral galaxy is a long conversation among stars. A coral reef is a long conversation among polyps and light. A human life is a long conversation among memories, bodies, and the world that sustains them. Each persists by moving, by exchanging, by letting the river of entropy do the work while guiding it into momentary design. There is comfort in this view. It suggests that our task is not to command order against chaos, but to keep learning how to pair them. We build habits that steady us, and we stay curious enough to revise them. We create institutions that protect and adapt. We craft art that honours what is fleeting by fixing it for a moment, then pass it on so it can live again in another mind. We make science that invites uncertainty in, tests it, and folds its lessons into better models. We treat each stable pattern as a bridge, not a fortress. The night sky, with its faint filaments and bright knots, is a reminder that there was never a single turning point when chaos yielded and order took over. The universe keeps choosing again and again, at every scale, to turn randomness into rhythm. That choice is not made once, it is made continuously. In that continuity we find our place. We are arrangements of atoms that manage for a while to be aware that we are arrangements of atoms. We are the pattern that can notice patterns. And so, if you carry one thought into sleep, let it be this simple and quiet one. When chaos became order, it became us. It became the stars that forged the elements in our blood, the cells that learned to coordinate, the minds that learned to imagine futures, the voices that learned to say thank you. Thank you for spending this time here, for sharing in this slow drift through the hidden scaffolding of things. May the patterns we traced settle gently, and may the soft hum of possibility stay with you as you rest. The universe will continue its quiet work without hurry, weaving and unweaving, opening space for what is new while holding what is old a little longer.